Welcome back. We have been talking about the energy balance expression for a general chemical reactor, and we were right midway through it. And so, the topic of the day will continue to be the design of chemical reactors, as it has been for several classes prior. Okay. So, we will directly go back to where we left you in the previous class, in the middle of the derivation. So, if you look at that, so we started with an energy balance expression, and I mean it is quite general, although we started with a Cstr. I mean for a batch reactor these terms will become 0, so on and so forth ultimately. So, we started with this assumption, I mean this particular concept, that energy accumulation is equals to energy flow in minus out plus heat transfer, rate of heat transfer from the reactor. It could be positive, it could be negative, and since this is a liquid reaction, so this PV goes to 0. So, internal energy you can replace by enthalpy, and then you have energy accumulation is nothing but this rate of change of the the different with time, the different species amount might change, and correspondingly their enthalpies will also change, because these enthalpies are per mole, be Na moles. So, it will be total enthalpy will be Na into Ha. Again we are not talking about total internal energy, which is U, we are talking about H, because H equals to U approximately. This PV tends to 0, because molar volume is very small when you are talking about the liquid state reactions. And then we had certain expressions that we replaced into this particular equation, and I mean that we used to replace the terms here in the particular equation, and ultimately we arrived at this expression for the energy balance. And this is a quite general expression, in the sense that if you have a steady state Cstr, then this term goes to 0, your temperature does not change with time. Your steady state batch reactor, this term goes to 0, because molar flow rate in is 0, and T0 is the temperature of inlet, okay, and this difference is the enthalpy of the reaction, and Ra you can replace by the concentration of A. Now, going ahead, if you now talk about a steady state Cstr, now we are going to go to the energy balance equation for steady state Cstr. We are more interested in Cstr because we observe steady state multiplicity here, which we do not observe in the batch reactors. So, if we rewrite this equation, this will be 0, then just this expression here for steady state Cstr, what you will get? It will be Fa0 Cpa T minus T0. So, this term is 0 minus delta H of reaction into Ra V equals to Q dot. Now, this Q dot, rate of heat transfer from the reactor, is nothing but small u, which is heat transfer coefficient of the reactor material, means the material which is used to prepare the to construct the reactor. So, this is the heat transfer coefficient of that material into the area of heat transfer multiplied by the difference in temperature between the coolant liquid and the reactor. So, that will be Tc minus T. T is the temperature of the reactor, and small u is the heat transfer coefficient, A is the area of heat transfer. Okay. So, now if you do a little bit of rearrangement and this okay, let me not skip any step. So, UA by Fa0 Tc minus T minus Cpa into T minus T0 minus delta H reaction into X equals to 0. This X is basically Ra into V. You remember that X is nothing but Fa0 minus Fa divided by Fa0. So, if you on both sides, if you divide by Fa0, then your Ra into V divided by Fa0, it is nothing but, because Ra into V is Fa0 minus Fa. So, it will be Fa0 minus Fa divided by Fa0, which is your conversion. Okay. So, the conversion now makes an appearance here. So, this can be rearranged as like this Cpa into UA divided by FA0 Cpa into Tc plus Cpa into T0, okay, minus Cpa into UA by Fa0 Cpa plus 1 into T minus delta H reaction into x equals to 0. Now, let us assume that this term is kappa, just replace this term with something else kappa, and let us define another term T prime, which will be equal to kappa Tc plus T0 divided by 1 plus kappa. This is just to simplify this expression. So, we are replacing this term with kappa. Now, this kappa basically it is what it is going to tell, this is heat transfer coefficient and this is the area of heat transfer. So, basically and what is this Cpa? Cpa is the heat capacity of A. So, this term tells you influence of heat exchange on reactor temperature. So, it actually tells you influence of heat exchange on the reactor temperature to that of the heat transfer fluid, that ratio, because you have a heat exchange during the process, right. Now, this heat exchange will basically influence the ratio of the reactor temperature to that of the heat transfer fluid. So, that is what is being given by this, because you know this UA, this is directly related to your reactor temperature also, because ultimately how much heat is being transferred, that is directly related to the temperature difference between the reactor and the coolant. And not only that, so that directly relates to also the heat transfer fluid, because the heat transfer fluid is the fluid to which the heat is being transferred. So, those information is contained here, those information are contained here. Also, if you are defining another term which is T prime, you see here this T prime is basically some kind of an average kind of thing between Tc and T0. So, this T prime will be something like an intermediate temperature between this feed temperature and the temperature of the heat transfer fluid. Okay. So, we are defining these two terms here. So, if we define these two terms and if we rearrange, you can actually work it out, then what will happen is you will get finally a very simplified expression which is minus delta H reaction into conversion equals to Cpa into 1 plus kappa into T minus T prime. Now, so this is the energy balance equation for a steady state Cstr. The left hand side, you see here this is conversion, here this is delta H of reaction, that is enthalpy of reaction. So, the left hand side basically tells you, this left hand side is rate of heat generation, which is nothing but GT. Remember that we had in the previous class, we had talked about this particular graph. So, this is GT, this is GT, the red one, rate of energy released or rate of heat generation, whatever. So, rate of heat generation for the reaction from the reaction mixture, that is this. So, this GT is this GT, that is the rate of heat generation, because ultimately how do you get these kind of graphs? You have to plot the GT as a function of T. So, you need to know that expression, because when you are operating a Cstr, you need to know what are the steady state conditions under that operating system or operating situation. So, you need to have this kind of graph. So, you need to generate that. In order to generate that, you have to have an expression of GT, that means the rate of heat generation as a function of T. This particular thing will give you that expression. So, here basically this is the rate of heat generation GT, the left hand side, because you know this x basically contains this information. This x is nothing but RAV divided by FA0, okay, because you know RAV is nothing but FA0 minus FA. So, that is FA0 minus FA divided by FA0 into x is equals to x. Now, this RA, this contains the temperature term, because the rate constant that is there, rate constant is equals to Arrhenius factor into exponential minus activation energy divided by RT, the temperature term comes there. So, that is the dependence of temperature that you get. So, that dependence of temperature. So, what you can do, you have this term, you just find out this term as a function of temperature. So, on the Excel sheet, what you can do is that on the you can actually plot your x, so your x axis and your y axis. Y axis is your GT and the x axis is your temperature. So, you have an expression of this as a function of temperature, and then you keep changing the temperature, you keep feeding different values, you get different values of this, the corresponding values of y. So, let us say you change the temperature from 290, 291, 292 like that, you go to say 500 Kelvin. So, correspondingly in the Excel sheet you can write down the formula of this GT, and then you can directly correlate with that particular box for the column of T. So, you have a column of T temperature, and then you have a column of GT, and you know the GT as a function of T. So, all these corresponding to each T value, you get the value of GT, and then you can construct this particular plot, which is like this. So, that is how you will construct this particular red plot. What is on the right side? Whatever is on the right side, this is basically your rate of heat removal, that is the heat transfer fluid removing the heat. Because if you are looking at this particular term here, what is this kappa? This kappa basically contains all this information. This U is the heat transfer coefficient, A is the area available for the heat transfer. So, those things are contained in this kappa here, and this T prime also contains kappa, and it also contains Tc. So, this heating characteristics or the cooling characteristics of the reactor, those things are basically contained here as far as the heat removal is concerned with respect to the heat transfer fluid. So, this term on the right hand side is basically your rate of heat removal, and both are equal. From the general expression of the energy balance, we assumed this equals to 0 because it is steady state condition Cstr, we assumed that, and then we derived. Once we have assumed steady state Cstr, ultimately what we will get, the temperature change with respect to time is 0, and that can happen if you arrive ultimately at this equation, that is rate of heat generation is basically equal to the rate of heat removal. That is what we have been always talking about here. And if you see this particular term, this particular expression is linear in T. So, if you are plotting this thing as a function of T, the reactor temperature, you will get a straight line like this. And if you see the left hand side, the expression of x, which is RAV by FA0, this expression is basically derived from mole balance equation. So, in deriving the left hand side, the final expression in terms of the temperature, you basically make use of mole balance equation. Although overall this is your energy balance equation, these things are important to keep in mind. So, ultimately you can use this particular term, get an expression of x as a function of T, and you can plot this as a function of T reactor temperature, and you get this curve, and this expression you plot as a function of T and you get this curve. And as you can see, as the T prime changes, the position of this graph also will change, and T prime is of course related to both Tc and T0. So, this will define different operating conditions. So, this line also will shift when you change this T0 and Tc, because T0 and Tc are contained both in this T prime, both of them are contained in this T prime. So, these are some subtle things that you have to keep in mind. So, this is the rate of heat generation, this is rate of heat removal. So, if you plot rate of heat removal as a function of temperature of the reactor, you will get a line like this. We have already talked about that, this line using a heat transfer fluid. As you keep increasing the temperature of the inlet, what happens is that if you put those values here, you will see this line will keep shifting to the right. So, this line, this rate of heat removal, that line shifts to the right as the temperature of the inlet goes up, temperature at the inlet, that is here. Okay. And correspondingly, if you are also plotting in the same graph, if let us plot also the GT, which is this side, this what you are getting on this side. Let us say it is something like this, it could be something like this. Okay. Here we have drawn several lines as far as the rate of heat removal is concerned, because we are considering several operating conditions. Here we only consider one operating condition, but this rate of heat generation, it has only one line, you are doing only one reaction. So, that is only one line. You can see that depending on your operating condition, your rate of heat removal will follow either this line or this line or this line. If it follows this line, there is only one point of intersection. So, if you are operating under this condition here, then you have only one steady state, because both of them have to intersect. If you are operating under this condition that is given by this line, you have actually 3 steady states. Again, if you are operating at this line, you have again 3 steady states like this. Okay. Now, let us go into some more detail of this situation. Okay. Let us now draw very carefully a graph where I will plot RT in the black and GT in the red. Okay. So, your RT is something like this. So, several values of RT are possible, I mean several lines like this, because as you keep changing the temperature, you can get this kind of lines. This is with increasing T0. Now, let us draw the curve of GT, a very specific way I am trying to draw this. I will draw this first and then I will explain to you. Let it go like this. Okay. So, because this is not to scale, so I just want to do it like this. Now, this curve, so you know that this is a GT curve that crosses these RT lines. These are at different inlet temperatures. Okay. Now, if you see the first line, it is crossed at only point, say let us say this is point 1. So, there is only one steady state for the first line. For the second line, oh, I am again taking the wrong pen, excuse me. So, for the second line, okay, so for the second line it crosses the second line, this is the second line, it crosses the second line at point 2. So, it crosses the second line at point 2. Point 2. In fact, it is better that we tell this point as point 2 because it crosses first and this point as point 3. So, basically for the second RT line your GT will cross it 2 times. So, that means for the second RT line you have 2 steady state points which is point 2 and point 3. Okay. So, for the third RT line, this is the RT line, for the third RT line, so this is point 3, now this is point 4, all right, and this is point 5, this is point 5. Let us draw this graph like this, because let us draw the graph like this. Okay, I will come to that after. So, this is 0.5, 4, 5, and then you have a point which is 0.6. So, basically this RT line and the GT line, they intersect at 3 points, 4, 5, 6. What about the fourth RT line? It is intersected at 0.7, at 0.8, somewhere here, let us say at 0.8. So, this is 0.6, that is 0.8, and at 0.9. And as far as 1, 2, 3, 4, 5. So, let us go to the fifth line. The fifth line, there is an intersection point with the red line which is GT. For the fifth line, let us say this is 10th point, and again it intersects at 11th point, and then for the sixth line there is only one intersection point which is 12. Okay. So, you see that depending on where this line of RT is, which is also being determined by this value of Tc and T0, coolant, your heat transfer fluid temperature and the temperature of your inlet, your line will change, and then either you may get only one steady state, you might also get 2 steady states, or you might get 3 steady states. Typically you will not get more than 3 steady states. So, then I can also draw a table like this. So, these are at different flow-in temperatures. Okay. So, this is temperature, reactor temperature, and let us say this particular graph is at a flow-in temperature of T01. This particular graph is at a flow-in temperature of T02. This is at T03. This is T04, T05, and T06. Okay. So, we can have a table like this. So, you have a flow-in temperature, that means the temperature at the inlet, whatever feed is there, what is the temperature of that feed. So, this is your flow-in temperature, and corresponding to that flow-in temperature there will be a steady state condition given by the temperature of the reactor, which means let us say you talk about this particular operating condition. So, where the flow-in temperature is T01, you see this line is generated when the flow-in temperature is T01, and this line is being cut by this red line which is for the rate of heat generation at 0.1. So, what is the temperature of this corresponding to 0.1 for the reactor temperature? So, this is the reactor temperature. At what temperature does this point correspond to as far as the reactor temperature is concerned? Let us say that is Ts1, S, because that is steady state. You know this point is a steady state point. So, what is the temperature corresponding to that steady state point of the reactor? This is the temperature of the reactor. So, that is Ts1, S designates steady state. So, for the flow in temperature T01, the corresponding reactor temperature that has to be attained for the attaining the steady state is Ts1. So, for T02 it is this line. So, you have basically for T02 you have basically two temperatures at which the reactor can attain steady state. So, those are Ts2 and Ts3, and correspondingly for T03, this is T03, there are three temperatures, corresponding temperatures on the x axis at which the steady state can be attained. So, that will be Ts4, Ts5, Ts6. That is why I have drawn the I have marked the points like that. This is 4, 5, 6, and for correspondingly for T04 the flow in temperature will generate this value of RT, this curve of RT. So, for that there are basically again three steady states, 0.7, 0.8 and 0.9, and the corresponding temperatures of the reactor, let us say Ts7, Ts8 and Ts9. Okay. So, like this you can go on. So, if you have constructed this particular graph, both the sides, because this is a steady state equation, and if you are plotting this as a function of temperature, then you are plotting this part, then you are getting this red line, you are plotting this part, then you are getting this line, and depending on where the temperature is, this T prime will, if you change this T prime, which is basically a combination, it has both Tc and T0. Tc is the temperature of the heat transfer fluid, T0 is the temperature of inlet at inlet. If you change that, then you can get basically your heat transfer lines, different heat transfer lines. So, at what point you will operate, at what temperature the reactor you will operate, that will also then depend on the temperature of the inlet as well as the temperature of the coolant or the heat transfer fluid, and correspondingly that will be designated by, say for example, if you are trying to operate at 0.4, this is a steady state situation, you are trying to operate at 0.4. So, in that case you should be on this line. So, you have to take the value of T0, that is the inlet temperature, as well as the heat transfer fluid, those temperature values you have to take corresponding to this line firstly, and secondly, if you have to operate at this point, your reactor temperature should be this temperature, and that temperature is Ts4, S indicating your steady state. So, that is why these are. So, if you are operating at a flow in temperature of T03, you have basically three different temperatures at which you can operate the reactor. At all these three temperatures the system will be in steady state. That is the idea of this particular graph. Now, if you look at it in some more detail, for example, if you are looking at, say I will draw the graph in a slightly more elaborate way, I will use the blue pen for this. So, let us look at this graph. Let us say this is your RT, this is your RT, and let us say this is your GT. Now, this is one particular line for the RT which corresponds to a particular T0 value and Tc value. Okay. You can have another line like this, you can have different lines like this. So, you can have a line like this, you can have a line like this, so on and so forth. Now, let us say we consider this particular line. So, we have basically three steady states. If you are considering this particular line, you have three steady states corresponding to that. Let me use the black pen for this. So, corresponding to this value of this line of RT, you have three steady states. So, 0.1, 0.2 and 0.3. Now, let us look at the steady state of 1. When you are at this particular point, your rate of heat transfer, rate of heat removal is equal to the rate of heat generation. Now, let us destabilize the system little bit. Let us increase the temperature of the reactors very slightly. So, if the temperature of the reactor increases, this x axis is the reactor temperature. So, then you will move somewhere on this direction. The moment you move in this direction, what will happen? Your red curve is basically below the blue curve. So, once you have come to this situation here, basically your at that point your RT is greater than GT, rate of heat removal is higher than the rate of heat generation. So, that would mean the reactor will immediately cool off. So, if you have heated slightly, the reactor will immediately cool off and it will go back to this steady state, because once you have come to this situation, your RT is basically higher than your GT. If you come to this side, you will see your RT is greater than GT. Okay. Now, what happens if you are at point 1 and if you cool down slightly? If you come slightly on this side, now your red curve is at a higher position than your blue curve. That means, if you have come slightly to the left, your GT is higher than RT. That means, rate of heat generation is higher than rate of heat removal. So, that means the reactor will heat up. So, under this condition, then the reactor will heat up and it will come back to this point 1. That means, this is a stable steady state. You slightly disturb on this side or that side, it will come back to its position. This is a stable steady state. So, what happens at steady state 3? You will have the same conclusion. You heat up little bit. Now, the heating curve, now the heat generation curve is at a lower position than the heat removal curve, which is blue curve. So, that means now the reactor will cool off and it will come back to this point. If you cool down little bit, then from this point you come to this side little bit. Once you have come to this side little bit, your red curve is basically higher, at a higher position than the blue curve. That means your rate of heat generation is higher than rate of heat removal. So, your reactor will heat up and it will come back to this position. So, this position, this point is also a stable steady state. What about this point? If you are at this particular point and if you are, say, if you heat up the system little bit, then what will happen? You will come to this position little bit here. So, if you are coming to this position, say you have this particular curve here, and let me elaborate further. So, this point is a stable steady state point, this point is also a stable steady state point. So, what will happen if you have this particular point here, if you are little bit off from this point, say you heat the system up a little bit, it has to go to a stable steady state ultimately, right. If you heat the system up a little bit, what you get here? If you heat the system up a little bit, you are going, say, from this point to this side. So, if you go from this point to this side, your heating curve is basically at a higher point than your cooling curve. So, if you heat up slightly, what will happen? The reactor will spontaneously heat up further and it will go to this point, because once you have come to this position little bit, your blue curve is basically lower than the red curve. So, if you heat up, the reactor will heat up further, because the rate of heat generation is higher, GT is higher than RT. So, it will spontaneously heat up and it will come to this particular point. Now, what happens if you cool down this system a little bit? If you cool down this system a little bit, say you come to this position somewhere here, you cool down the system little bit, you come to this position somewhere here, what will happen? Your blue curve is now at a higher position than your red curve. So, basically your rate of cooling or rate of heat removal is higher than the rate of heat generation. So, it will then spontaneously cool off further and it will go to this particular point. So, ultimately that means this particular steady state that you have, is an unstable steady state. It is an unstable steady state. So, if you heat up little bit, it goes to the higher steady state. If you cool down little bit, then it goes to the lower steady state. So, when you have this kind of 3 steady states, typically what you will get is the higher steady state and the lower steady state will be stable and the middle steady state will be unstable. And very frequently at the lower steady state your conversion is very small, at the higher steady state your conversion is quite high. In the middle range you will typically have to work sometimes, because although this curve is exaggerated, many times the temperature of the higher steady state is much at a higher value, much higher value. So, it is difficult to control. So, maybe you want to work in the middle steady state, but you have to be very careful so as not to disturb it, otherwise it will go away from this unstable steady state. So, what we will do is we will stop here and we will continue to discuss this situation a little bit further in the next class. Till then, thank you and goodbye.